Let me ask you something simple. Which is bigger, the number of even numbers or the number of whole numbers? Your instinct probably says all numbers. Obviously, even numbers are just half of them, but you're wrong. They're exactly the same size, and that's not even the strange part, because some infinities are larger than the others, and the proof is so simple that a child can follow, but the implications broke mathematics. And to understand this, we need to go back to 1891. A German mathematician named George Cantor sat down and asked a simple question that nobody asked before. Not what is infinity that philosophers asked and argued for centuries, but can you measure and compare infinities? His colleagues might have thought that he was insane. The great mathematician of the time, Henri Poincaré, called his work a disease corrupting mathematics. Cantor suffered multiple nervous breakdowns and he died in a sanitarium in 1918, but he was right. And the proof he discovered, called the diagonal argument, which is one of the most elegant and devastating pieces of logic. Let's build it from scratch. So first we need to agree on what it means for two collections to be the same size. This sounds obvious, but stay with me, because this single idea is the entire foundation of what comes next. So how do you know these two groups have the same number of things? You count them, right? But counting only works for finite things. What Cantor did is you don't count them, but you pair them up. So if you can match every element in group 1 to exactly one element in the other group with nothing left out, then they are the same size. And mathematician calls this one-to-one correspondence a bijection. Every number on the left pairs perfectly with an even number on the right. 1 pairs with 2, 2 with 4, 3 with 6, and so on. So by Cantor's definition, there are exactly as many even numbers as there are whole numbers. I know that feels wrong, but hold that feeling, because it's about to get even much worse. Cantor called this type of infinity countable infinity, or the Aleph null, the smallest infinite cardinal number, and it is the infinity of anything you could in principle list one by one. The whole numbers, the even numbers, the odd numbers, even the fractions. Here some values are repeated, for example 2 over 2, 3 over 3, 4 over 4, that always gives you 1. If you exclude all of these numbers, so if we exclude the 1 in brackets that repeats the same value, you are left with an infinite set of unique rational numbers. So there is one-to-one correspondence. Every fraction gets a number. So fractions, despite seeming increasingly more dense than the whole numbers, are actually the same size of infinity. So here is a question Cantor asked next. Is every infinity the same size? Is there only one infinity, or is there something beyond the Aleph null? And this will follow the diagonal argument, and you need to pay close attention. This is one of the most beautiful proofs in mathematics. So let's ask a simple question. Can we list all real numbers between 0 and 1? Real numbers are things like 0.5, 0.333, and so on. Just the ones between 0 and 1. It seems manageable, right? Cantor said, assume you can. Assume someone hands you a complete list of every real number between 0 and 1, all listed out one by one. So it doesn't matter what the list looks like. Any list, the most carefully constructed list imaginable. Cantor then does something extraordinary. He builds a new number using the diagonal argument. So he gets the C read, which is by picking up the first digit from the C1, second digit from the C2, the third digit from the C3. So I want you to think about this for yourself for a second. You have these diagonal digits and you want to build a number that is different than any number on the list. So what is the most natural thing you can do is just add 1 in every digit. So this is exactly what he did. He obtained the C red from the digits that we circled with red. Then he added 1 to each and every digit. So your new number disagrees with the C1 in the first digit, C2 in the second digit, C3 on the third, and so on. So it disagrees with every single number on the list. There's one thing to be careful. If you hit 9, you write 0 or 1, whatever you like. But we assumed the list was complete. We assumed it contained everything. So no matter how cleverly you write your list, we can always construct a number that's not on the list. The real numbers can't be listed. They cannot be counted. They are fundamentally larger infinity than the whole whole numbers. Cantor called this cardinality of continuum. Then he proved that there are infinitely many infinities, each larger than the last. Think about what just happened. We did not use telescopes, we did not run experiments. We just sat down with a pure logic and proved that the universe contains different sizes of something that has no end. Cantor's colleagues called this madness. Poincaré called this a disease in mathematics, but today it sits at the foundation of modern mathematics. And if you want to go deeper, Cantor's work leads to one of the most famous unsolved problems in mathematics, the continuum hypothesis. It was at the top of the David Hilbert's legendary list of unsolved problems. We still don't know the answer, not because we haven't tried, but because it was proven that we cannot know the answer. If this ignites your curiosity, subscribe to Breaking Spacetime, and I will see you in the next one.